Okay, hello and welcome back to question 3 of the British Algorithmic Olympiad 2022 round 1. And if you haven't seen the videos for question 1 and 2, then I've got full explanations of them on the StudyWave YouTube channel. If you have, then make sure to check out the GitHub repo with all of the code for these questions. We have a Discord community for people who are preparing for this exam so they can connect with each other. And also our website link is also down below. Okay, so let's jump into question 3, pairs and triples. Pythagorean triples are positive integral solutions ABC to the equation a squared plus b squared equals c squared, as everyone probably knows since they were like 12 or something. For example, 3, 4, 5 and 15, 36, 39. Okay, so these are just some examples of solutions. The first of these is an example of a primitive Pythagorean triple, as no positive integer divides a, b, and c, whereas 3 divides a, b, and c in the second example. Okay, so we can see that 3, 4, and 5 are all co-prime, but 15 over 3 is 5, 36 over 3 is 12, and 39 all over 3 is 13. So 5, 12, 13 would be an example of a primitive triple. Okay, so then although this theorem, as it relates to right-angled triangles, is attributed to the Greek mathematician Pythagoras, blah, blah, blah. Okay, so this paragraph is basically just some historical waffle to try and confuse you. Okay, so let's actually jump into part A for 2 marks. Show that for integers x, y, the integer x squared minus y squared is odd or a multiple of 4. And if you try to do this question, then you probably would have saw in the mark scheme over here of like this quite long-winded way, and over here at the bottom it also says allow any suitable mathematical proof using modular arithmetic. So I'm going to show you how that would look like using modular arithmetic, because this solution is already good using the other way. So we have x squared minus y squared. And what I want you to consider is every single number in the world is either a multiple of 4, 1 more than a multiple of 4, 2 more, or 3 more, if it's an integer, obviously. So let's make a table of these possible numbers. So if we consider n mod 4, then n can either be 0, 1, 2, or 3, obviously, right? And then if we consider n squared mod 4, then what can this be? So 0 squared is still 0, 1 squared is still 1, 2 squared is 4, which is the same as 0 mod 4, so this is 0, 3 squared is 9, which is 1 more than 8, and 8 is a multiple of 4, so this is 1 mod 4. So now we can clearly see that every single square number is either a multiple of 4 or 1 more than a multiple of 4. So now we can basically say, okay, therefore squares always 0 or 1 more than a multiple of 4. So now if we were to actually brute force all cases for x squared minus y squared mod 4, it would look like this. So we could have 1 minus 0, which is equal to 1 mod 4, which is odd. Then we could also have 0 minus 1, which is equal to minus 1, which is equal to 3 mod 4, which is odd. And then we also have 0 minus 0, which is equal to 0 mod 4, which is a multiple of 4, so multiple of 4. And then we also have 1 minus 1, which is also 0 mod 4, which is also a multiple of 4. So now we can see that in all the cases for what x squared and y squared can be mod 4, these are all of the cases, then it's always either going to be odd or it's going to be a multiple of 4. And this is exactly what we wanted to show. So that's pretty much it. Okay, move on to the next question. Okay, question B for 8 marks. Suppose ABC is a primitive Pythagorean triple, i.e. a squared plus b squared equals c squared, where a, b, and c are all integers that have no factor all in common. So basically a, b, and c are all coprime. As at least one of a or b is odd, let's assume that b is odd. Okay, because remember that if a and b were both even, then that would mean that c is even, but then that would mean that a, b, and c is even so that they would all have a common factor of 2, but then that would mean that it's not primitive because they have a factor in common. So that means naturally one of them is going to have to be odd. And you should have been able to deduce this even without the clue in the question, but they've kind of already told you. And it said, since a and b are kind of symmetric, it doesn't matter which one is which. They've just said, okay, let's assume b is odd. Okay, carrying on. Let c plus b all over a equals m all over n, where m all over n is a fraction in its lowest terms. So then again, m and n can't be simplified, they're coprime, and we've basically set that equal to this. Okay. First find b all over a in terms of m and n, and using this, find a, b, and c in terms of m and n. And then verify that any positive integer pair mn provides a solution to the equation a squared plus b squared equals c squared. Okay, so we'll do this part later. This part is at the end. For now, let's focus on finding b all over a in terms of m all over n. So our goal now is to somehow manipulate the two equations that we're given. So we're given this and we're given this, and we want to somehow manipulate them to find b all over a just in terms of m and n. Okay, so this was part A for question 3. Now for part B. So we know that a squared plus b squared is equal to c squared. And what else do we know? Well, we also know that c plus b all over a is equal to m all over n. So these are the two like factual things that we're given. So everything else that we're doing now is just going to be deductions. So what's the first thing that we can do? Well, notice that we can bring b squared to the other side, and now this is quite nice because this is actually a difference of 2 squares. And now what we can say is there is a c plus b here and there's a c plus b in the numerator here. So we want to kind of link these because cancelling these out might be nice. So now let's multiply by a on this equation and we get am all over n. And now notice that we can basically sub this into here. So a squared now becomes c minus b times am all over n. And now notice that there is an a over here and this is a squared, so there's an a in common. And since, if we go back to the question, a primitive Pythagorean triple, if we go to the definition, they are positive integral solutions. So that means that a is not going to be 0, so we don't have to worry about that case. So we can just go ahead and divide by a. And then we can say a is equal to c minus b times m all over n. And we can say that a is not equal to 0. What can we say next? Well, notice how there is a c here, and there's also a c here. So that means we could definitely get rid of this c. Because ultimately we want to just get b and a by themselves. We want to get rid of c. That is our end goal. So now what we can do is we can say, okay, c is equal to am all over n minus b by simply bringing the b to the other side. And now plugging in this c into here, we're going to get a is equal to am all over n minus b, and then minus another b from here. So we can simplify that straight away to just minus 2b, and this is m all over n. And now remember, our end goal is to get b all over a. And this step might have been a bit difficult to notice, but if you did, then well done. But if you didn't, don't worry about it too much, because already doing this has gotten you a decent amount of marks. so we divide by a. So we divide through by a, this cancels out. Then we get 2b all over a, m all over n. And now what we can do is we can multiply by n all over m to cancel this. So we're going to get n all over m is equal to m all over n minus 2b all over a. And this is very good because now we have b all over a by itself. So this is a good sign that we're on the right track. So now we can rearrange to get 2b all over a is equal to m all over n minus n all over m. So I've simply brought this to that side, and I've brought this to that side, a little swapperoo. And this implies that b all over a is equal to half times m all over n minus n all over m. And this is the same as if we just put this as one fraction, we get m squared minus n squared all over mn. And I can actually bring this a half into here. So this is kind of one part that we've done now. Okay, so now that we've done this, we can go back to the question and say, okay, so we've done this now. That's good. And now the next step is using this, we have to find a, b, and c in terms of m and n. So you might be thinking, why did they ask us to find b all over a? What if we found c all over a as well? What would happen? So let's do that. And generally, you're not really going to know where to go in these problems. You're going to do a lot of trial and error. It definitely took me some trial and error, but if you just keep being suspicious and try out different things, eventually you will get somewhere. So again, using the fact that they've given us c plus b all over a is equal to m all over n. So this is the same thing as over here. This is given to us. Then we're again going to multiply by a to get a m all over n. And now we know, well, what we can do now is we can use this thing that's in this box, and we can get b by itself in terms of a. So we can basically get rid of this b, because remember, we want to find c all over a. So our goal is to get rid of the b. So now what we can say is, okay, b is equal to a all over 2 times m all over n minus n all over m. And all I've done here is I've taken this equation and I've multiplied by a on both sides. And now what we can do is we can put this b into here. So we can say c plus a all over 2 times m all over n minus n all over m is equal to 8m all over n. Now we can expand, so we have 8m all over 2n minus an all over 2m, which is equal to 8m all over n. And then notice that there's an am all over n and am all over 2n over here. So we can simplify that. And that's going to end up with c is equal to am all over 2n plus an all over 2m. And then this can be factored as a half of mn plus n all over m. Oops, that m is a bit crazy. And then half. And then we can again do m squared plus n squared all over 2mn. Okay, so that's equal to oh yeah, so this there's actually an a here. Remember, we have to take out a all over 2. And then this is equal to a times that. And now c all over a is simply just m squared plus n squared all over 2mn. Now at this point, we know that c all over a is equal to this. And we also know that b all over a is equal to m squared minus n squared all over 2mn. So we know these two things. And I mean, technically the question says just find using a, b, and c in terms of m and n. It doesn't say anything about simplifying, like, explicitly. I mean, if you're doing an Olympiad, it's kind of like implied that you have to simplify. But then at this point, you could literally just say they both have a denominator of a, and it's also 2mn. So we can just say that, we can just set a is equal to 2mn. A is equal to 2mn. C, we can say b is equal to m squared minus n squared. Oops, let me write that. And then c is equal to m squared plus n squared. And this is actually completely valid. We can definitely do this. But the only issue is that these fractions, these fractions are in its simplest form, because remember that they're all co-prime. And another thing is that these fractions are not necessarily in their simplest form. We don't know that for sure. And I'm not actually entirely sure how to prove this rigorously. I'm not going to try come up with a proof that is a bit wiffly-waffly. But essentially you can just go to the mark scheme, and it says they've given kind of an explanation here as to why this is in its simplest form. But to be honest, I'm not really happy with this mark scheme. I feel like it could be a little bit more detailed. Like, one thing I want to know is why m squared minus n squared and mn are definitely co-prime. And if you know the answer to that, definitely put it in the comment section. I'll be interested to see why. But then also, if you want to research more about this, this is not like a unique question. This is called the Pythagorean generating function, I think, or something like that. So if you want to learn more about it, you can just look into this. Okay, and then the final step is just to verify that our solution works. So simply, if we just actually plug in what we found into a squared plus b squared equals c squared, and we have a squared plus b squared is equal to c squared, then we have 2mn squared plus m squared minus n squared all squared. Expanding these, we have 4m squared n squared plus m to the 4 minus 2m squared n squared plus n to the 4. Then this can be simplified as m to the 4 plus 2m squared n squared plus n to the 4. And then this can be written as, notice that this is a square, so then we can say m squared plus n squared all squared, which is equal to c squared, so it satisfies. So that works. And yeah, that's everything for which question is this. This is question B, and let's move on to question C. Okay, part C for 11 marks. Write a program to calculate C of n, the number of pairs of non-negative integers alpha beta, such that alpha squared plus beta squared is less than n, where n is in between 2 and that big number. The single input will be the value for n. Okay, so the first thing in this question is you should have part A and part B in the back of your mind. And don't worry if you couldn't figure out how to do this question and now you're thinking that, there's going to be some simple way to do this using the previous parts. Personally, I didn't do that. I used a bit of a different approach. But then just general advice, keep part A and part B in the back of your mind for questions like this. But for me personally, I used an approach that uses circles. And the main reason I came up with that is because when I saw this reminded me a lot about the equation of a circle, which is just x squared plus y squared is equal to r squared. So in this situation, n is equal to r squared, so root n is equal to the radius. And so what can we do now? Well, let's actually try to do some drawing now. And I'm going to get the squared paper to keep things as clear as possible. So let's say part C. And what I'm going to do is I'm going to draw some axes. The only difference is that I'm not going to draw the axes for the negative parts, because remember that over here it says alpha and beta are non-negative integers. So we don't really need to worry about the negative parts. So instead we can just focus on a quarter of a circle. So let's draw some lattice points, and I'm going to draw them 2 spaces apart just to try and keep these points a bit more clear. And let's consider the case where n is equal to 5. So the radius is root 5, so it's going to have to pass through this point and this point. So let's draw that in. Oops, that's the rubber. So we go through here, here, and here. And notice that this problem of finding pairs of numbers is equivalent to counting how many points are inside and not on the boundary, because look here, it's a strict sign. It's not less than or equal to, but it's less than. So how many points are inside the circle but not on the circle? So convince yourself that this is an equivalent problem, because we basically want to find, this problem can be translated to finding all of the radiuses that are less than root n. That's basically what the problem is. So now that we know this, we can start thinking about how we're actually going to calculate this. Now in the case that n is equal to root 5, the radius is, or n is equal to 5, then the radius is equal to root 5. So 2 points that we can fairly easily calculate are these, and similarly by reflection these. So these 2 points are easy to calculate because all we have to do is we have to say, okay, what is root 5? Well, it's in between 2 and 3. It's slightly more than 2. So all we have to do is we have to take the ceiling of it and then take away 1. So in this case, the ceiling of root 5 is equal to 3, and we want to take away 1 to get 2. And the reason that we're doing this, instead of, for example, taking something like the floor, because we also could take we could take the floor of root 5, and this would also be equal to 2. But the issue is that this wouldn't work for integer radiuses. So in the case that n is equal to 9, for example, then this would look like, actually I'll do it for 2 because it's a bit easier to draw. So in the case that n is equal to 4, so radius is equal to 2, it would look like this. Now again, r is equal to 2, so we would be taking the floor of root 4, which is just 2, but then again, we don't want to include this boundary point. So this means that we would be counting both of these, but we only want to count this one. Whereas if we take the floor, if we take the ceiling of root 4, well, this is equal to 3, and then minus 1, this is equal to 2 again, because the floor and the ceiling in this case are both the same, because it's an integer, and we minus 1, then we get 1, which is exactly what we want. So that's why we have to use this formula over here. So now that we know this, we can easily calculate these points over here. And we can also easily plus 1 to get the origin, because the origin is basically always going to be inside of it. So now, if we want to get the boundary points, we have the ceiling of root n times 2, because we want to get both of them on both of the x and y axes, and then plus 1. So we have this so far. But now the tricky part is calculating the points that are inside. Now how do we do that? Well, let me draw a bigger quarter circle. So this one has radius 1, 2, 3. 3 squared plus 1 squared is 10. So this has root 10. So in this case, n is equal to 10, and the radius is root 10 for this most outer circle. And let me get rid of these. And basically what we can do now is we can ignore all of these and just focus on calculating the ones inside the circle over here. Now one thing we can do is we can say, okay, so the radius is n, or the radius is root n, but we want the radius to be slightly smaller than root n. So what we can do is we can take n minus 1 and then we can square root it. And this will basically be the next smallest radius that we can actually use. And if this happens to somehow be an integer, then we'll count it. But if it's not an integer, then it's fine. And basically what we're going to do now is we're going to compute all of the possible heights for the radius. So notice if we take this radius, then this has height 1. If we take this radius, it has height 2 because there's a height of 2, so it's quite self-explanatory. And then for this one, there's a height of 3. But then notice that we're not actually taking this point. We're taking a point that is very close. So it's the square root of 1 less than the radius squared. So in reality, we're going to be taking the radiuses that are like this. So they're all going to be slightly more than the actual radius. They're going to be slightly less than the actual radius. And basically what we're doing is we're computing their heights. So we're iterating using their heights. And then we're rounding down to find their base. And their base is how many points are inside of the quarter circle. So in this first one over here, in this lowest triangle, notice that the base is 2. Well, it's a bit more than 2, but we're rounding down. So we're taking the floor of the base. Then again over here, in this larger triangle, it's again, the base is slightly more than 2, but we're rounding down. So again, we're going to be calculating, we're going to include these 2 points and these 2 points. But then you can see in the next one, the base is slightly less than 1. So that means that we're going to round down to 0 and we're not going to count any points on this level. And we're basically going to do that for all of the heights, and that's how it's going to work. So now if we actually, this is quite confusing, but if we actually open the code editor now, so I've got the code editor, and if you look at part C, now I've said that this is basically just a variant of Gauss's circle problem. So this is actually a very famous problem, but they've put a slight twist on it, saying that it could only be a quarter circle, and also in Gauss's problem you can include the points that are on the circle. In this case, we can't actually include them. And what I'm doing here, so I'm taking in n, so this is the radius squared, which can be a long, because remember it's greater than 2 to the 32, so it has to be a long. We're inputting it, and then we're getting the upper bound. So remember, the upper bound is the thing that I told you before, where we take the ceiling of the square root of n and then minus 1. So this finds how many points are inside of the quarter circle that are on the axes. And then over here is again what I told you. So there's two axes, so we're counting the points on the axes, and then this is counting the origin. And then this for loop is doing the thing that I told you with the heights. So it's iterating through every single height of a radius that is slightly less than the actual radius. So this is what I was telling you before. So n is the radius squared, and we're minusing 1 to find the radius that is slightly less than the actual radius. Because remember, it's a strict sign, strict inequality sign. And what we're doing is we're iterating starting from a height of 1, because remember, we don't want to start from a height of 0, because this is, we already counted the height of 0 in the upper bound. And we're iterating until we hit the upper bound. So this is a less than sign, so until we hit the actual upper bound. And on every single iteration, we're adding the floor. So this is going to get converted to the floor function implicitly, because this is rounding down to a long, or a long double in this case. And we're taking the square root of 1 slightly less than the radius. So slightly less than the radius squared, this is what this is. And then this is the base, or the height squared. And then once we take the square root of that, we're going to get the base squared, and we're going to truncate that, which is the equivalent of taking the floor, because in this case, taking the floor and truncating the decimal is the same, because we're working with positive numbers here. And yeah, it's a bit difficult to understand. My explanation might not be the best, but I think if you just stare long enough at the diagrams I've made and at this code, then it should definitely click for you. And then we just output the lattice points. So if we actually go to the mark scheme, and let's just get the last input case, and we put it in, and then we compile, so we can say g++ 3.cpp, and then a.out. We can see that we get the final answer, which should be the same as this. Yes, it is the same. Ends in 6.8, ends in 6.8. And you can see that this is incredibly fast. And you might have tried to do solutions where you literally manually check every single point or something like that, but this is definitely the fastest way of doing this. Okay, that's everything for question C. Let's move on to part D. Okay, part D for 1 mark. Now, getting this 1 mark, like, I bet it was actually probably the hardest, one of the hardest questions. Like, I don't think many people got this mark. But the fact that it's 1 mark, it means you probably don't really have to think about it too much. And if you got the insight in the previous question of this idea of using circles, I think that there's a slight chance you might have actually got this. Now, again, if we go to part D, and if you just consider, so I'm going to actually copy this diagram and paste, and I'm going to scroll down a bit, and I'm going to get rid of these points, or these line segments. And first of all, what is C of n? So C of n is counting the number of pairs inside of the circle. So that's what it's doing. So if we actually think about this, we're basically counting the number of boxes inside of the circle. So, for example, if we let each point be the bottom left of a square, then we have this. So this is the box that represents the bottom left of the origin. And then we have this, and we have we have this, because remember, it goes slightly outside, but that's fine. And we have this, then we have this, this, and this. And also for this point, we also need another one over here. Now, yeah, with this diagram, it's looking more like a square or a rectangle currently, but that's only because we don't have that many points. You can kind of see that as the circle gets very, very big, there's only going to be not that many things sticking out. It's going to be more or less on point with the actual quarter circle. So one thing that we can say is the number of points is tending towards the area of this quarter circle. So what can we say? Well, we can say C of n is basically, for large n, is going to become pi all over 4n. And the reason it's pi over 4n is because the equation of a circle in radians is r squared theta. Well, r squared theta is the equation of a sector, with angle theta. And also, just even if you didn't know that, pi r squared is just the formula for a circle. And since this is the whole circle, we only want to get 1/4 of the circle. And then what is r squared in this case? Well, r squared is equal to n, so this is equal to pi 4 all over n. So that's why this equation, actually I'm not going to rub that out. I'm just going to move it to the side. That's why this equation holds true for large n. And then we can simply just rearrange it to get Cn all over n is pi over 4. And that's it for question D. Okay, part E for 3 marks. Suppose C1 of n is the number of pairs of integers alpha beta such that one of alpha and beta is negative and the other is non-negative, and alpha squared plus beta squared is less than n, where n is not a perfect square. Okay, there's a lot of information to process there. So one of them is negative. So without loss of generality, let's just say that alpha is less than 0, and the other is non-negative, so one of them is greater than or equal to 0. And equivalently, we could also have beta is less than 0 or alpha is greater than or equal to 0, because it says either one. Well, it says one of alpha and beta. So it doesn't matter about the order. And n is not a perfect square. Okay. And then a ceiling function can be written as this, which I already explained in part C, which denotes the smallest integer not smaller than x. Yeah, that makes sense. Given that t of n is equal to the ceiling of n, construct an expression for c1 of n in terms of the function c and t. Okay, so the first thing to do is to draw a diagram. And again, we're going to relate this to circles. So here we have alpha is less than 0 and beta is greater than or equal to 0. So basically we want them to be the opposite. So if we consider the 4 quadrants, here alpha and beta is positive, so we don't want this. Here, let's just say x and y, it doesn't matter. X is less than 0 and y is greater than 0, so this is good. Here they're both negative, so this is bad, and then again this is good, because y is negative and x is positive. So we only want to consider the second and the fourth quadrant. So let's make this a bit smaller. Is it going to let me make it smaller? Come on. Let's just delete it. And what can we say now? So let's actually draw the axes. So that's the y-axis, and this is the x-axis. Is it gonna... Let me draw straight. Okay, it's not collaborating. Okay, there we go. A straight line. So then let's just draw some points. So 1, 2, 3. So then 1, 2, 3. So we can fill these out. Yes, it's a bit repetitive and annoying, but in the real exam you have to do this as well. And nearly done. So again, let's consider the case where n is equal to 5, so the radius is root 5. So that means it's going to pass through which point? It's going to pass through here and here. So we'll do it like this. We can get rid of these circles. And then over here, it's going to pass like this. So here are 2 quarter circles. And remember that C of n from part C, so if we scroll up again, from part C, remember, C of n calculates how many points are inside of a quarter circle. But the thing is that over here, we want, first of all, remember the conditions. We want alpha is greater than 0, greater than or equal to 0, and beta is less than 0, or alpha is less than 0, and beta is greater than or equal to 0. But the only issue is that if we look at these points over here, these points are, we have that, so for example, again, switching it to x and y, we have that x is greater than or equal to 0, which is fine, but but y is equal to 0. So in this case, yeah, x is greater than or equal to 0, but y is equal to 0. So that's bad, so we don't want these points. And then similarly over here, we have that x is less than 0, which is fine. Or actually, what do we want? We want that y is greater than or equal to 0, not rubbing out. Y is greater than or equal to 0, which is fine, because they're greater than or equal to 0. But then over here, x is, in this circle over here, I'm going to redraw it. Not erase, I'm going to redraw it like this. Come on, just redraw. Okay, there we go. So, in this circle, x is 0. So we want it to be less than 0. So that's a problem. So we want to get rid of these points. Now remember, when we calculate C of n, we're going to overcount this twice. This point is going to be counted twice. So if we remove it, so that means we have to remove it twice as well, because we don't want this point. So okay, so the first thing is to actually calculate all of the points inside using C of n. So we're going to do 2 times C of n. And now we want to get rid of these. Well, including the origin. And how do we do that? Well, in this case, n is equal to 5, r is equal to root 5. So we want to get rid of 3 points. And we want to get rid of 3 points twice. So how do we do that? Well, the ceiling of root 5 is equal to what? It's equal to 3. So this works perfectly. Similarly, if we were to have something like this circle, which I think is root 10, because we have 1, 2, 3, and then width 1, so 3 squared plus 1 squared is equal to 10. So yeah, this is root 10. Then if we have the ceiling of root 10, then this is well, root 10 is slightly more than 3, so this is equal to 4. And we have 1, 2, 3, 4. So yeah, we can see that generally this works for counting those points that we want to get rid of. So now, all we have to do, if I move this to the side, is we just have to put this in brackets and get rid of the square of the ceiling of root n. And again, using the notation they've given us, this is equal to C of n minus t of root n. Because they've simply renamed the ceiling function to t of n for some reason. And this is equal to C1 of n. And yeah, that's how you answer part E. And that's the end of question 2 of the British Algorithmic Olympiad 2022 round 1. And I'll see you in the final question.